Hello, my name's Darren Holmes, and today we're going to be using the Primer Trainer and looking at lesson number 4, 8-bit addition. So under new instructions, we're going to use the add C instruction with an opcode of 81, and it says the C register is added to the A register with the result being stored in the A register. Now the Z, S, P, CY, and AC flags are affected. So today we're going to have to talk about the flags in the flag register. We're also going to use the move command. We've seen the move command before, but now we're going to move B into A, and its opcode is 78, and the contents of the B register are copied to the A register. No flags are affected. So this is the first lesson where we've actually affected some of the flags in the flag register. So on page 740 of your textbook, we have the ADD command, add register to accumulator. It's 1 byte, 1 machine cycle, and 4 T-states. Checking the hex code, we want to do an ADD-C. So the code for that is 81. We have the description where it says the contents of the operand, register, or memory are added to the contents of the accumulator, and the result is stored in the accumulator. If the operand is a memory location, that is indicated by the 16-bit address in the HL register pair. Under flags, it says all flags are modified to reflect the result of the addition. So I want to refer you back to page 31 of your textbook, where we have the introduction to the 8085 assembly language programming. And on page 32, section 2.1, they give us the 8085 programming model, where they tell us that we have the registers. So we've got the A register followed by the flag register. And down here they have the flag registers. They have D7, which is the high order bit, is the sign. And we have D6, which is the 0 flag. D4 is an auxiliary carry. D2 is parity. And D0 is the carry bit. So on page 33, they have a fair size write-up on flags. It says the ALU includes 5 flip-flops which are set or reset after an operation according to data conditions of the result in the accumulator and other registers. So they're called the 0, the carry, the sign, parity, auxiliary carry flags. It says down here, these flags have critical importance in the decision-making process of the microprocessor. And they give you an example of the jump on carry. So far we've just looked at the jump command, and that was just a straight command that jumped back to FF01. In this case it's going to be a decision-making command, and we have that to look forward to in a later lesson. So on page 34 they have table 2.1, and it talks about the 8085 flags. So the 0 flag is set to 1 when the result is 0, otherwise it is reset. The CY or carry flag, if an arithmetic operation results in a carry, the CY flag is set, otherwise it is reset. Sign. The sign flag is set if D7 of the result equals 1. Otherwise it is reset. Parity. If the result has an even number of 1s, the flag is set. For an odd number of 1s, the flag is reset. The auxiliary carry. In arithmetic operation, when a carry is generated by digit D3 and passed to digit D4, the AC flag is set. So this isn't byte plus byte, this is nibble plus nibble. So if the result of the two nibbles is greater, then we're going to have an auxiliary carry flag. Section 6.2 of your textbook talks about arithmetic operations. And you'll notice one of them is the add command, add immediate, subtract, subtract immediate, increment, and decrement. And your textbook gives you an example, 6.3, of using the ADD instruction that you may want to review. You may wish to reference Schaum's Outlines, Digital Principles, 3rd edition that we used in our Digital Systems course. And on page 170, they talk about binary arithmetic, and you can see they talk about binary addition. And they give you an example here where you're adding 1 plus 1, the result is 0, and we move the carry up. And then we add the carry into the next set of numbers until we get to the end. So in here we're just using 2 bits, so we had A and B, and the output was the sum and the carry out. So just a little review for you from your Digital Systems course. So looking at lesson 4, it says this program adds the B and C register together and stores the result in the A register. It says this is done by copying the value of B to A and then adding the value of C to A. So they've given us the assembly language listing, and once again we're going to start at address FF01. We're going to move B into A. So now A is a copy of B. We're going to add C to A, and then we're going to return control to the monitor operating system with the restart 7 command. You can see that they've given us the opcodes 78, 81, and FF. So this should be a fairly short program to enter into the Primer Trainer. So to enter the program into the Primer Trainer, starting at FF01, I'm going to type in 7, 8, increment, 8, 1, increment, FF, increment. And then I'm going to hit the reset key. Okay, so looking at the procedure, we're going to test the ADD instruction. We're going to load the program into memory, which we just did. Press the reset button and do the following. It says the B and C registers will be loaded with numbers whose sum will not be greater than 9, so that the result will not have to be translated to decimal to see that the instruction worked properly. So we're going to load the BC register pair with 0403, which is the same as loading B with 4 and C with 3, and then we're going to run the program. The program will stop at FF03 because of the restart 7 instruction. Now it says here, because the microprocessor is so fast, the program stops almost immediately. So you may think that it did actually run the program, but by examining the registers we will see that it did. If you examine the A register, we will see that it has the value 7, and if you convert the flag register to binary, you will see that bit 0, the carry flag, is 0, which means the result of the addition was small enough to fit in the A register. So to load the BC register pair, we say function B, and in there we're going to put in 0403. We press enter, and it brings us back to FF01. We can check the register. Function BC 4 and 3 did get loaded. So I'm going to press function run, and it did run pretty darn quick. So now I'm going to check the accumulator. So I'm going to say function A, and you'll notice that it's 7. And I believe 4 plus 3 is equal to 7. Now you'll notice the flag register is 0, 0. So the first 4 bits are 0, the second 4 bits are 0. So that means the carry flag was indeed reset to 0. So under step 2 of the procedure, we're going to press the reset button and load the BC register pair with FFFF, then run the program. When the program stops at FF03, we're to examine the A register and flag register. It says we will see that the A register is now FE, and that the bit 0 of the flag register, the carry flag, is now 1, which indicates that the result of the addition was too big to fit in the A register. So I'm pressing the reset key. That brings us back to FF01, pressing function B, and you'll notice the BC register pair was cleared when I hit the reset button. We're to load in FFFF, press enter, and then we're to press function run. And now I want to check the A and flag registers, so we press function A. And we can see that the result is FE, but the flag register is now 9-1. So we need to decode the flag register. So looking at the results from the AF register pair, we can see the A register has our math result of FE that we were expecting. The flag register has the result of 9-1. Now, in order to determine which flag bits were set, we need to decode the 9-1. So I like to draw these little boxes and write down what each flag register is. So we have the sign, the 0, the auxiliary carry, the parity, and the carry bits. So 9 is 1, 0, 0, 1. And 1 is 0, 0, 0, 1. So you can see the carry bit was set, the parity bit was reset, the auxiliary carry was set, the 0 bit is reset, and the sign bit is set. So let's look at the calculation and see what actually happened inside our ALU. So we took FF, which is 111, 111, and we added it to FF, which is 111, 111. So looking at the binary math, 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. And 1 plus 1 plus 1 is 1, carry the 1. That is the auxiliary carry bit. So that bit got set. Then again, 1 plus 1 plus 1 is equal to 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. And finally, 1 plus 1 plus 1 is 1, carry the 1. And that is our carry bit being set. Then our sign bit is set by the most significant digit of our answer. So that is a 1. So our sign bit gets set. Now the 0 flag is set to 1 when the result is 0. Otherwise it's reset. So you can see our result is not 0. So our 0 flag is reset. Then our parity flag. If the result has an even number of 1s, the flag is set. For an odd number of 1s, the flag is reset. So you can see in our result we have 1, 2, 3, 4, 5, 6, 7 1s. And 7 is an odd number, so our parity bit is 0. Now you'll notice we have 1, 2, 3 flags that have no meaning to them. These are undocumented flags. You'll notice that they are 0. So the 8085 does have these undocumented flags, and they also have some undocumented opcodes too. So I just want to show those to you. So if you do a Google search on the 8085 undocumented instructions, you're going to come up with a few results. I just want to show a few of these to you. The first one is what undocumented 8085 instructions is Stephen Morse referring to in the beginning, right? So he wrote a little web page and talked about the beginning of computers. So this is from Retro Computing, and that first document, this is the document in the beginning by Stephen Morse. That was October 1980, and he talks about Intel creating the 4004 and 8008. So as you search down here, you can find that there's answers to these undocumented instructions. And you can see that we have the K flag and the V flag, as well as a few jump instructions. Now they mention another name in here, Ken Sharif. So if we go to his blog, and he has a very interesting blog, many topics. He's a very knowledgeable person. It's kind of hard to do a search on his blog, but if you go to Google and type in right2.com 8085, he's got Silicon Reverse Engineering, the 8085's undocumented flags, and he talks about the V and the K flag and how they're set. He also talks about the circuits for the K and V flags. So he's actually got pictures of the internal silicon workings of the IC. Extremely interesting blog. And one last place I want to show you is one called Electronic Error, and they have the undocumented 8085 instructions. So he starts off with the flag register, and then he comes down with the undocumented instructions. However, the RIM and SIM instructions are documented, and we will be using them later for serial communication. But he does talk about the other instructions. So this is interesting information that you may want to pick up and read about on your leisure. I just want to summarize the flag registers that we've talked about today. In version 1.2 of the Primer Simulator, I have labeled each of the bits in the flag register, but keep in mind only 5 of them are documented flag bits. So we have the sign, the 0, the auxiliary carry, the parity, and the carry bit. The 3 undocumented flags, the K, the 0, and the V, are always going to be 0 in my Primer Simulator. Now today we learned about undocumented flags and that there are undocumented commands within the 8085. But keep in mind, if you start using these, they're not guaranteed to work the same for every single 8085 manufactured, because some of them were manufactured by different companies. So it's not good programming practice to use these, but you're more than welcome to try them out. You'll not damage your Primer Trainer doing so. So to review Lesson 4, 8-bit addition, we're going to be using the Primer Simulator. You'll notice it's on version 1.2. So if you go to Help and About PSIM, you can see version 1, we fixed the breakpoint problem. And in version 1.2, the undocumented flags we're going to set to 0. So V is set to 0 and K is set to 0. So we're going to start by turning on the simulator. And the first thing we need to do is to load in the program. And then we're going to reset the trainer to FF01. And then under procedure number 1, we're going to load the BC register pair with 0, 4, 0, 3. And press enter. And then we're going to press function run. And then we're going to check the A and F register pair. So you can see that 4 plus 3 is equal to 7. And none of the bits were set. Remember, in the simulator, you can go to View, Register Contents, and you can see all the flag bits are reset. We're going to reset the simulator, and then under Procedure, step number 2, we're going to load into the BC register pair, FF, FF, press enter, function run, and then we're going to check the AF register pair. You can see the result is the same as on the primer trainer. We have FE, and the flag register is set to 9-1. To decode it quickly, we can go to View, Register Contents, and bringing down the register contents, you can see the sign bit is set to 1. The auxiliary carry was set to 1. And the carry bit is set to 1, indicating that the result is larger than the size of the accumulator, which was 8 bits in size. So this concludes lesson number 4. In lesson number 5, we're going to be looking at 8-bit subtraction. So don't forget to subscribe so that you don't miss any of our lessons.